I'm going to be giving my final presentation of senior seminar on music and how it's described mathematically, and it's primarily described using waves. The reason we use waves is because the atmospheric pressure, molecules all close together, millions of them all close together and bouncing off each other and creating atmospheric pressure. And whenever something vibrates, it causes a change in the pressure around that vibration. It's increasing and decreasing periodically air pressure, changes in the air pressure, that is. And so whenever that change in air pressure travels through space or any medium, really, and it enters into our ears are designed as long tubes that coil around and amplify these tiny little waves that travel through space. And inside of our eardrum, we have then three little bones that pick up these frequencies, and they resonate at certain frequencies. And according to the resonating that they produce, it taps on what's called our basilar membrane, which is basically this flat membrane that's stretched across two sides of our inner ear, and different parts of it vibrate at different frequencies. And so that's what we perceive as sound, and sounds of different pitches and different volumes. So we use sine waves to describe music, because that's how our bodies perceive it. I should say it's okay. So we have our inner ear, right? It's this tube that kind of coils in, and it has this center, right? Well, across it, like I described, we have this membrane. Actually, it's farther in, but I don't want to get too far away. But it's this membrane that, if you think about it, in two planes, it's kind of stretched. It's got like little tendrils here, and it stretches from thin to thick like this. So as frequencies come in of varying as waves of different frequencies or amplitudes come in, then different localized spot of this membrane will vibrate in this axis, in the z-axis. So if you look at it like this, it's a simple harmonic motion. Here's our equilibrium point, and then at a certain point along it vibrates harmonically. And so the solution to the harmonic equation is y equals cosine of the square root of kt. And anyway, it's sines and cosine waves combinations. It's a linear combination of sine and cosine waves, and that's why we use sine and cosine waves, specifically those, instead of some other periodic function, to describe music. It's simply because of the membrane that we use. And it's not even simple harmonic, it's forced, damped harmonic motion, because we have fluid in our ears that dampens it, and we have, it's not perfectly elastic, our membrane isn't, and so it's not as simple as that, but it's fundamentally that idea, that it's sine and cosine, a linear combination of them. And the idea of linearity is actually it's a big deal as far as the wave equation in general, not even just as a simple harmonic motion. So anyway, that's why we use sine and cosine waves. And so for a lot of the rest of the semester, I talked about the wave equation. Now the wave equation is it's in it's the second derivative. It's not the first derivative. It's the measure of the change of acceleration of a part. Like, for instance, I'll just draw it out. We have a wave here, right? right? And so what we're saying is that for any point along this x-axis, then its acceleration, the speed at which it changes, will or the rate at which its speed changes, is proportional to its curvature. So at this part of the map, its downward forces here and its left to right forces here are related. And that's I guess the reason why we use this. I guess I don't want to get off track here, but anyway, so the solution I talked about this earlier. The solution is just it has to do with separating the variables because it's part of a family of partial differential equations that allows you to separate the variables, which I don't fully understand. I'd like to. I think that we kind of started touching on it in real analysis this semester about why you are able to, why these have this property. I can't justify it mathematically, but I know that linearity is huge. The ability to separate this equation into functions that are just functions of one variable, as opposed to two. So let me go ahead and write this general solution to the wave equation. So we have here a wave equation which equals the second derivative of y with respect to t equals c squared, which is just what they call the wave constant. And all that is just the specific size and speed that the wave is traveling at. Specific one for that individual wave. This is with respect to x with position. And this is with respect to time, t squared. Okay, so this is the wave equation, right? Actually, I should put WE, I suppose. Wave equation, right? And its general solution is of the form a linear combination of y equals f of x plus ct, which is just, and this is x minus ct. And what these are called transport equations, right? It means that this is the part of the wave that's moving forward, and this is the part of the wave that's moving backwards. And what's cool about this is that any wave can be described as a combination of these two, as a combination of a wave traveling one way and then another wave traveling another way. They're all just some variation. They're all just some linear combination of that. And so I talked about, I derived the general solution and gave, justification as to why it was true. And then I moved on towards trying to apply it to different instruments. Because I didn't want to stick too long in just theory if it wasn't related to music. So what I ended up doing was going through different types of instruments and trying to relate how the wave equation described that instrument. And so I started with the vibration of a string, which is the simplest case. You have two endpoints and you have a string in the middle, right? And you say a guitar string and you pluck it, well then it vibrates. It vibrates all across that string at a certain frequency and amplitude and produces a certain note. Well, when you zoom in at an infinitesimal little part, you see that, here's your equilibrium, right? And your string kind of comes up. I'm just zooming in. I'm just zooming in here. So you have your string and you have your, tension right here and your tension right here, and you have, all these forces that are pulling it. Like you have, actually, the tension goes this way. I don't have my picture in front of me, and I need my picture. But anyway, in one dimension, you zoom in and you see it, with the small angle identity, we see here that this tangent right here, the tangent of this curve is equal to sine. Anyway, so you get to derive, and you put in your boundary conditions, like how short the string is, or the thickness of the string, and you can describe the frequency that it's going to vibrate at according to the wave equation. And then I moved on beyond the string to describe a drum head, which is two dimensions instead of just a string, right, fixed on endpoints. You have, a radius, and so it's vibrating across the whole head. And I looked up, different kinds of drum heads, and ones that are tightened to different tensions, and how they changed the the solutions to the equation. And we also looked at some drum heads that were vibrated to certain specific harmonic frequencies. And what it would do, this is part of it that I didn't understand because it was part of the harmonic series that I didn't have time to investigate. But what it was like at one particular node, like say the first member of the harmonic series would be like it would vibrate. They throw sand on the top of the drum, and it would all collect. It would all collect here, right? And this little ring on the inside would be empty, right? I'm not going to draw it that way. I'm just going to draw where it's blank to assume that it's full of sand, and then where I draw the line, that's where it clears. So it vibrates, right? And it vibrates and shakes the sand off of this area and into the middle and to the edges. And then the next one was like it creates two little nodes. And then the next one, there was some other one that was like it created like that, and then it separated on the inside. So it's like it resonated here, and then it resonated within itself. Anyway, it was cool. We looked at a lot of those because those were just really interesting. Or just really interesting to see visually how and where these things are resonating. So we looked at that a lot. The two-dimensional drum head stuff was real interesting to us. And there were some that like you could like if it wasn't circular, you could by parts you could see like what frequency as a whole, what it vibrated at by taking its piecewise frequencies. That one was not as fun, but it was still interesting to think that you could describe something that's not uniform. Okay, so wind instruments, what it does, like for instance, say a French horn, or let's just say a clarinet, like you have your thing, you have your bell, right, and you have your buttons. Okay, so it has this whole inner chamber here that's closed off. And so it's more than just the vibration that comes out of the bell here, or out of wherever, I don't know where clarinets emit their sound. But it's a combination of the initial pitch, right, and the air that's contained in the bell. And this is all instruments, horns and flutes and saxophones, anything that contains air and it has air being pushed through it. It's a combination of that initial sound wavelength combined with the what's it called, pressure, the atmospheric pressure, and how the wave goes through that, and the way that they interact. And so, like, say there's differences between instruments that are closed off, like the clarinet is, or open at the end, like a flute is. A flute is just a bar, and it's just got a hole in the end. So instead of the waves coming down and then bouncing back, the waves just keep going out, and they don't have any kind of they don't resonate with themselves in the way that other instruments do. And so that was really interesting to me too. And then we talked about as a capstone to the whole multi-dimensional wave equation. And we looked very briefly at things like bells, which are like a drum head, right? But instead of what we assume as minuscule thickness, instead it's some significant measurable distance, like a church bell. It's not just some little thing. It's sometimes 3, 4, 5 inches thick. So it's a variable worth taking into account. And so we didn't get too much into that, but it has an effect. It has an effect on how on the waves that are transmitted by that instrument. But there was something else that I wanted. I thought it would be cool. Here, that'll be my capstone. The last thing we did was acoustics, and that's in 3 dimensions. The wave equation in 3 dimensions, in X, Y, and Z, as position, as its position part of the equation, because it's in 2 parts. It's separated as a function of time and as a function of position, because it's separable. Its position is in X, Y, Z. It's in a triplet form. So anyway, that would represent acoustics, as it travels through air, which is a pretty simple idea. And the thing is, with all of these, with no matter how many variables we're dealing with, all of the solutions to them are superposition of, it's a linear combination of the separated states of its a general solution, like if arbitrary functions that are superposed. Well, I shouldn't say arbitrary. The general solution is arbitrary functions determined by initial boundary conditions. And so the last thing, my last closing thought that I wanted to think about, I thought this is so cool that we think of a concert bass drum, right? Like one of those giant, 48-inch drums, huge drum, and the thing's huge, right? So it's got this giant, it's closed on either side. It's got a head on one side and a head on the other side. And so it's like a wind instrument. It's got a closed area, but it's also acoustics in there. And so I thought just a giant double-headed drum like that is just so cool, because it combines the wave equation in 2 dimensions and the wave equation in 3 dimensions. I just thought it was cool, and I would love to be able to investigate how all of those different, how the different elements of the sound that's being created, how in the minutia it's created. The combination of the initial strike of the head, and then how the head resonates, and then how it pushes the air through that medium, through those acoustics, and hits the other drum head, makes that vibrate, and that sends that back. Meanwhile, the air on the inside has already been reflected back, and now the drum head vibrates. The other one I would just love to see how the combination of all those things works. Like what in the nitty gritty makes it sound the way it does. I would just love to see it. So that's most of what I talked about with the wave equation. I talked about equal temperament just very, very briefly, but that's not really what I want to talk about today because a lot of this semester's focus for me, because I took quantum mechanics also and real analysis, and so we dealt with waves and we dealt with infinite sums a lot, and so that's kind of the focus of where my mind has been a lot this semester. So that's where I want to kind of end on. I investigated very briefly some of Fourier analysis, and in general, what it is just a decomposition of any periodic wave into a sum of smaller parts, usually an infinite sum. And what we can do with this is that it allows us to say, like, the first example that I saw that kind of made sense is that, we have this square wave right here, and it's not really a naturally occurring wave. It's just an abstract construct that we created. But anyway, what we can do is we can decompose this into an approximation. And I don't have the numbers written down, or else I would give you the specifics. But with the first iteration of its Fourier's decomposition, if you just take that first coefficient and you graph that, then it would be an approximation. It would be an approximation of the square wave, right? Still discontinuous at these points with a vertical shift here, but a wave here, a short wave. And then the next one would be, I'll make it a little smaller, would be a much smaller wave excuse me. It would be a much smaller wave that had more frequencies and a smaller, it was a higher frequency, I should say. And it would be smaller. What it is it's converging to, as this more and more terms are added, then this will slowly converge closer and closer and closer until finally we have our square wave. Of course, this is as n approaches infinity. It converges to it. It doesn't ever actually equal it. Now, this is where Dr. Sarvash would perhaps disagree with me. But as it approaches infinity, it will converge to the square wave. Not uniformly because it's discontinuous, but piecewise it will. So that's kind of really the only real work that I did with analysis. I mainly just kind of did it, I just kind of took it as a concept because with sums, there's a whole lot of variations of different kinds of functions and different kinds of decompositions, and they don't all converge. They don't all converge. The ones that converge might converge just piecewise. A lot of them, that's the only convergence they do get because, like for instance, the square wave that I showed, the saw wave that does like this, or I guess you could say these don't really, if you look at it just like that, it's not continuous here, and it just kind of, but this also can be approximated with Fourier analysis. It would look something like this. It would look like a wave. And then, I guess actually these are here. And then it would be like and then the next one would be, a sharper, steeper, and a higher frequency wave like that. So, and like I said, I don't have the specific coefficients right here. I just have the pictures in my head. So what it communicates to me is that to a certain degree, we can represent a sound wave, any sound wave, an arbitrary sound wave. The timbre of every instrument, of any sound, the timbre of it can be described as a Fourier transform. They call it a Fourier transform because And by design, periodic functions don't have a beginning and they don't have an end. And so they call it a Fourier transform to kind of put these finite bounds on it, and then to approximate it still using the Fourier coefficients. Anyway, so a sound wave, or the sound wave of any timbre, of any frequency, of any kind, can be decomposed, and we can see its individual, its characteristic, its timbre, according to its Fourier coefficients. And I just think that's fascinating. I love it. I think that's so amazing. It's just a representation of the uniqueness of every sound that exists, and I think that's just amazing. And I kind of want to follow that up with what we were learning in quantum mechanics, that these subatomic particles also behave like waves, for the most part, until they don't. And that in the same way that the normal wave equation is linear, and the general solutions are superpositions of different stationary states, is what they call them in quantum mechanics. So that's what's in stationary states. They call that because the time-independent Schrödinger equation, which only means the Schrödinger equation that's been separated into independent functions of position and time. They call it the time-independent Schrödinger equation, and it's all that we work with, because it's the only way that we can provide a general solution to the Schrödinger equation. And so we separated out time-independent Schrödinger equation, and we always time-independent Schrödinger equation. It has general solutions, and these general solutions, they tell us the probability of finding a particle in a general region of a domain during a certain interval of time. It's not it's not precise at all, and it's predicated entirely on continuous probability distributions and just the ideas of continuums in general. It's the only way that we can justify the shaky ground that quantum mechanics gives us. Well, anyway, I just think it's fascinating that we're learning the exact same stuff in quantum mechanics, that these particles that vibrate at certain frequencies, at certain points in time, that those vibrations can be described. Well, I don't want to say predicted, because that's not the right word. But anyway, that they all also have their own individual characteristic breakdown. We lump them together into certain classes, but I think it's cool to think that every particle in the universe has its own timbre, as it were, its own characteristic wave form, wave state, or whatever. I just think that's fascinating. It's fascinating to think that it's individual, that it's characteristic to itself, that it has its unique decomposition, its Fourier transform, as it were, though I'm sure it's not constrained by whatever Fourier would try to come up with that it is. Of course, in real analysis, we proved the foundation upon which the ideas of infinite sums and linearity and convergence and the being able to break down a wave into an expansion, a power series expansion even, and it's all fascinating to me. But I think that really the biggest impact that all of this has had on me is to think that everything has its own unique decomposition, its own characteristic equation, wave state that determines its timbre. And that's all I've got. I hope that you enjoy it, Dr. Mabry, and I hope that you have a good summer, a good semester, and I will see you and talk with you later. Bye now.